Hey guys, welcome to the Biomechanics 1 lecture video series. So one part that you guys should be relatively familiar with by now, we've covered quite a bit, is calculation of vectors. So remember, if I have some kind of object, and it really can be any object, it can be a body or some brick or a square, and it might have various forces acting on it. We are ultimately interested in the resultant of that, right? So in this case, I have two forces and they're both acting on an object, and where's the resultant of those forces going to be? So in order to find out what this resultant is, we tend to use what's called the component method, and we've gone through this in class, where we deconstruct any given force into its x and y components. So you see here, this would be force, let's call this force A, and this is force B. We deconstruct these forces by plotting them on a Cartesian plane, and then we decompose it into its x and its y components, right? So we'll get the magnitude here of AY, and we'll get the magnitude here of AX. The same thing would be true with this vector B. So we'll deconstruct that into its x and y components. And then therefore this would be by, and this here is bx. The way in which we find the magnitude of by and, so this should be bx and by, as well as ay and ax, is that we take the angle that it makes with the horizontal into consideration. Okay, so if I just redraw this vector A, and I try and decompose it into its x and y components relative to this angle theta. If I wanted to find a y, it's the angle that's opposite, and I've got the hypotenuse. And if you are confused about what's the opposite and hypotenuse and adjacent, then please look at one of the other previous videos that covers it quite in detail. For now, I'm just going to kind of breeze through it. In essence, the sine of an angle is equal to the opposite divided by the hypotenuse, which in this case, if I use the labels, would be ay over a. Therefore ay, if I multiply a out to the other side, a sine of that angle would give me what the ay component is. Okay, the ax component utilizes the cosine function, which is the adjacent divided by the hypotenuse. Again, if I use the labels that I've implemented here, it would be ax over a, multiply that over to the other side, so the a cosine theta is going to be equal to the ax component. Right, and now it's all follow the same principle with the b vector, but in essence what you'll find is this trend that tends to emerge, right? The b vector would also be classified as b sine of its angle, which in this case might be something else, let's say phi, would be the y component, and b times the cosine of its angle would give me the bx component. And the same trend will tend to follow through all the time. So we could kind of summarize it as follows. So whenever we look at the vertical component of a vector, it's always going to be the magnitude, right, of whatever the actual vector is itself times the sine of whatever angle it makes with the horizontal. And similarly, the horizontal component is always the magnitude of the vector times the cosine of the angle that it tends to make with the horizontal. Okay, so in order to allow you guys to practice this type of application, as well as incorporating multiple forces, anything between 2 to 5, so let's say we had some scenario such as this. I have 4 forces acting on an object, It can be any object, we'll just call this M. As long as I'm given the angles with which they tend to act and the magnitude of the forces, my interest in these types of examples is always to find the resultant. Okay, so to allow you guys to practice that, I've just created this kind of simple interaction that allows you to test as many examples as you possibly want. You can see it'll generate some sample values, some sample force values, and some sample angles. And you might be thinking to yourself, hey, oh, hang on, Mark, I've never dealt with anything with 147 and negative 134. Well, in essence, what this does is, let me just explain it one more time, is an angle in that application is always given from the horizontal. And remember, it can rotate through a full 360 degrees. So if I have my axis, my coordinate axis, remember that rotation in the anti-clockwise direction is always positive, and rotation in the clockwise direction is always negative, right, relative to this starting point over here. So if I give an angle of, let's say, 60 degrees, positive 60 degrees, it would look something like this. I would get a force vector and it would be at 60 degrees. If I give a value of 110 degrees, well, this is 90. So 110 would be somewhere along here. So it would be rotation relative to the horizontal in the clockwise direction of 110 degrees. And you might be like, well, how do I deconstruct this into horizontal and vertical components? Remember, there's 180 degrees in every straight line. So if this is 110, then this here should be 70. So I can use the same principles and decompose. If this was, let's say, vector C, this would be the vertical component and this would be the horizontal component. I can still construct the triangle, except I use the angle of 70 to calculate the mathematics. Let's say I had something along the lines of negative 40. So it means it's rotating in the clockwise direction. So negative 40 might look something like this, right? And negative, let's say, 150 would look something along these lines. So again, it would be rotation in this direction. This would be 150, negative indicating just the direction. So that means that this angle over here would be 30. And again, I could deconstruct something into its horizontal and vertical components, right? So if this was vector D, then this would be dy and this would be dx. Okay, so hopefully that makes sense. Let me just take you back to that quickly. So you can choose how many vectors you want to include. So like I said, anywhere between 2 and 5. It will randomly, every time that you press the F9 key on your keyboard, it would generate new values. You'd have to write them down, because every single time that you press any button, it's going to generate new values, and it'll do that infinitely, so you can work through as many examples as you possibly want to. And then you'd have to write them down in this, because the computer will use this to derive the correct answer. Okay, so write it down, write it in here. I've just taken a sample already. In this case, a vector of magnitude 288 in terms of force at an angle of 60. That's the one that you can see over here. And then a magnitude of 360 at an angle of 110. That's the one that you tend to see here. So what we want to do now is find out what the resultant is. So you'll have to work it out on paper, plonk your answers in here, work all your answers out to the nearest 2 decimal places, and once you've put all your answers in, it will reveal what the solution is here, and it's going to give you immediate feedback to tell you if it was right. And then you could always go back and see where you were wrong. So if I deconstruct this, I'm going to show you how I work through it, and then we'll take it from there. Okay, so I've kind of just plotted it in here so long. So let me just write down the values quickly. So I had just got to find out where we are. There we go. So I had 2 forces. Force number, we'll call it A, had a magnitude of 288 newtons and acting at 60 degrees. And I had B at 360 magnitude of 360 acting at 110 degrees. Okay, so the 60, like I said, just to make it abundantly clear, was taken as this, was my 60 degrees, and then my 110 degrees was also taken relative to the horizontal, so this over here is 110 degrees. But in essence that means this angle over here is 70 degrees, right? So I could deconstruct this force vector into its vertical and horizontal components, and I could deconstruct this force vector into its vertical and horizontal components, right, using the respective angles. That'll make it easier for me to calculate. Okay, so let's go with vector A first. Let me just make it abundantly clear again that this is the one I've labeled vector A, and this is the one I've labeled vector B. Okay, so let me just quickly make that obvious, and I'll use that. This is vector A. Okay, so if I deconstruct everything into vertical and horizontal components, I say I'll do all my vertical maths first, then I'll do all my horizontal maths. That's just the way I prefer it. I mean, it can be up to you. So if I look for vector A, vertical component is always the magnitude of the force times the sine. So this will be 288 times the sine of 60, right, which will give me 249.42. 249.42. If I take the horizontal component, it will be 288 times the cosine of 60, which is 144. Good. Then I'll do the same thing with vector B. It's 360 times the sine of 70, which is equal to 338.29. 338.29, and this is 360 times the cosine of 70, which is equal to 123.13. 123.13. But there's something that we have to check, right? Our convention, as per usual, is anything acting up and to the right is given a positive value, therefore anything acting to the left and down is given a negative value, right? Okay, so vector A is acting to the right and up, so its horizontal value is given a positive sign and its vertical component is given a positive sign. Vector B, however, is acting to the left and up, so its vertical component is given a positive value and its horizontal is given a negative value. So if I add these two components together, I would get 587.71, and then I take the positive 144 and I subtract 123.13, and I get 20.87. Alright, so this gives me the coordinates, or the magnitudes of the x and y of my resultant triangle. So the resultant triangle would look something like this. It's acting to the right because it's positive of 2.87 and upwards with a magnitude of 587.71, which means that my resultant should be acting something like this at some angle, right? This would be my resultant. So how do I find the resultant given two sides? I use Pythagoras. So r is going to be the square root of 587.71 squared plus this 20.87 squared, and that's going to give me a resultant value of 588.08. 588.08. Now I just need to know its direction. Remember, any vector has both magnitude and direction. Well, I have to find this angle. I have two sides, the opposite and the adjacent side, so I'll be able to use the tan of that angle is going to be the opposite over the adjacent, which is going to be equal to 587.71 over 20.87. So to find the angle on its own, on your calculator you just inverse tan this particular value, and you should get what your angle is, which is equal to 87.97. 87.97 degrees, right? So I have all the components that I need for my answer. Now I just need to check if my calculations were right. So here's the 4 components that I need to plug in to that particular application and see if I'm right. So let's just go back there. Okay, so the resultant vertical component we said was 587.71. The resultant horizontal component we said was 20.87. The resultant we said was 588.08, and the angle we said was 87.97. Remember, all your answers have to be to 2 decimal places. Once you press enter, it's going to tell you whether you're right or not, and it's going to draw it out for you. Okay, so just to prove, and it's going to give you the answers here, so it's going to tell you what the y component, x component, resultant vector, and angle should have been. Let's say I made some mistake and I entered 25 here by mistake. So you can see here that's where I put a wrong answer, and I might need to go back and solve for it. But the answer is already given here, so if I just put this 20.87 in there, it should be right. It's also going to tell you what quadrant the resultant vector is ultimately going to be in. So I could do the same thing, like I said, by adding 3 or 4 vectors. Now all of a sudden I get different options in terms of what I can possibly place in here. So let me just take this one over here, 454, and acting at an angle of 92, 454, acting at an angle of 92. And let's make some negative one. Let's say this 90 at negative 153, 90 at negative 153. So you can see here at the end of the day it's going to show me where these force vectors are. It's going to already give me the answers. If I put answers in here, I'll just delete it and try and work through it myself. So you can see here I've got different forces acting at all kinds of different angles, and then I'll try and solve what the answer ultimately is. So if I just put some random answers in here, you should see that all my answers are wrong. I've just randomly plugged it in, but it'll show you what the right answer should ultimately have been. Okay. So, like I said, it's going to generate an infinite number of examples. Write them down, work your way through it, right, step by step, and then at the end of the day, place your answers in here and see where you went wrong. Okay. So hopefully that makes sense. Hopefully it's a useful type of an application. Like I said, the method of analysis here becomes really, really important, because for you to solve resultant vectors is going to be really, really important going forward. Alright, that's it for now. Thanks for watching.